There are a few organic compounds, such as benzene, in which electrons are shared between three or more atoms. Those are called delocalized electrons. Lewis structures do not show delocalized electrons. This is where resonance structures comes in. In general chemistry, we looked at different types of solids. Some solid types involve localized electrons. Let's see if you remember solids. Stop the video and answer these three questions. And the answers are: remember, a covalent bond forms with one unpaired electron from one atom combines with one unpaired electron from another atom. The two electrons in the bonding pair are shared between two atoms only. The localized electrons in covalent network solids such as diamond give rise to its properties hard, high melting point, and an insulator. In general chemistry, we looked at a solid type in which electrons are shared between three or more atoms. Those are called delocalized electrons. Stop the video and answer these two questions. And the answers are: in a metal, electrons are shared between many metal atoms. Those delocalized electrons help us explain why metals are soft and are conductors. Let's take a look at an organic compound. Benzene is a very common organic compound. Here is the Lewis structure. Note that the Lewis structure shows 3 carbon-carbon single bonds and 3 carbon-carbon double bonds. Experiments show that a carbon-carbon single bond is longer than a carbon-carbon double bond. However, with benzene, experiments show there are 6 carbon-carbon bonds of the same length. The Lewis structure does not match the experimental data. Here's the explanation. The electrons in the carbon-carbon double bond are not shared by 2 carbon atoms only. The electrons in the carbon-carbon double bonds are shared by 6 carbons. Those electrons are delocalized. One Lewis structure of benzene does not show delocalized electrons. However, 2 Lewis structures in which a carbon-carbon double bond in one structure is replaced by a carbon-carbon single bond in another structure, and vice versa, represent delocalized electrons. These 2 Lewis structures are called resonance structures. The double-sided arrow tells us that those 2 structures are resonance structures. So remember, one Lewis structure shows localized electrons only. Resonance structures are 2 or more Lewis structures. Each resonance structure has the same bonding or same connectivity. The difference between resonance structures is that double bonds or lone pairs or charged change positions. Here are 2 examples of compounds that are represented by resonance structures. Stop the video and answer these questions. And the answers are: let's apply our knowledge of bonding and structure. You're looking at the IR spectra of salicylic acid and 1-propene-3-ol. The carbon-carbon double bond peak in salicylic acid is at a lower energy than the carbon-carbon double bond peak in 1-propene-3-ol. Stop the video and explain that observation. And the answer is: the delocalized electrons in the carbon-carbon double bond in the salicylic acid ring lead to a slightly longer and weaker carbon-carbon double bond than the carbon-carbon double bond in 1-propene-3-ol. The longer and weaker carbon-carbon double bond in salicylic acid is easier to stretch, therefore lower energy in the IR spectrum. This is something scientists do. Given experimental data, determine the structure. Stop the video, review the experimental data, and then draw the structure of the compound. And the answer is: this structure fits 1 and 2. This carbon has a tetrahedral shape, so each HCH bond angle is the tetrahedral bond angle of 109.5 degrees. The same is true for each CCH bond angle. This Lewis structure shows a carbon-oxygen single bond and a carbon-oxygen double bond. They are not the same length. That does not fit the experimental data, but delocalized electrons and resonance structures explains experimental data 3. This table shows the bond length and bond strength of various bond types. Bond length is the distance between atoms. Bond strength is the energy required to break that bond or the energy released when that bond forms. Stop the video, review the table, and try to figure out the relationship between bond length and bond strength. And the answer is: the closer the atoms are together, the stronger the bond. For example, a carbon-carbon double bond is shorter than a carbon-carbon single bond, but the carbon-carbon double bond is stronger than the carbon-carbon single bond. Bond strength tells us how reactive the compound is. Would you expect explosives to have strong bonds or weak bonds? Stop the video and think about that for a minute. Here's an example. Nitrogen triiodide, Ni3, decomposes explosively with a touch of a feather. Since only the touch of a feather is needed, that tells us the Ni bonds in nitrogen triode must be weak. The nitrogen iodine bond energy is very small, 169 kilojoules per mole. That's the energy of a feather. A nitrogen-nitrogen triple bond forms. A lot of energy is released when that bond forms. I2 also forms, but not much energy is released when that bond forms. In the Ni3 explosive, not much energy is required to break the weak bonds to make it decompose. When the strong nitrogen-nitrogen triple bond forms, a lot of energy is released. Compare the energy required to break bonds to the energy released when bonds formed. This results in a very exothermic reaction, which occurs very fast, which causes the explosion. We will look at the speed or rate of reactions later. So let's review. Stop the video and answer these questions. And the answers are: bond strength tells about reactivity and whether a reaction is exothermic or endothermic. What about bond length? Stop the video and answer this question. And the answer is: so how atoms bond together tells us about structure. Bond types tells us about reactivity.